All right, folks, in this video we're going to talk about some of the basic properties of radicals. This first one is the nth root of a product A times B, and the result here can be found by simply breaking that up as the nth root of A times the nth root of B by taking the root or radical of each of the factors separately. We should note here in red, note, and I shouldn't say note, I should say warning. The nth root of A plus B is not the nth root of A plus the nth root of B. To illustrate this, I'm going to go through the following. Did you guys know that the number 5 is the square root of 25? True or false? You'd probably say true to that. And if you did say true to that, you'd be correct. Did you also know that underneath the radical, 25 is 16 plus 9? True or false? If you said true to that one, you're also correct because that's true. And then the square root of 16 plus the square root of 9. And then the square root of 16 is, that's right, 4. The square root of 9 is 3. And 4 plus 3, true or false, equals 7. And that's true. What just happened? Is 5 equal to 7? And the answer there is no, they're not. So what happened? And it happened right here. You cannot break up the radical across addition. So be careful. You can do it with multiplication, and it turns out you can do it up here with division as well. That is to say, if you're going to take the nth root of a fraction, you can do the nth root of the numerator over the nth root of the denominator. So those are our basic properties. So let's talk about an instance of simplifying some fractions here. Oh, I'm going to change this one a little bit. Let's see. Square root of 72 over 35. Let's do that one. Yeah, that's good. Okay, so starting with A here, we have, this is supposed to be the letter A. Starting with the letter A, we have the negative root of 64. Well, the square root of 64, how can we do that? I need a number. Let's say that's equal to negative k, where k squared is equal to 64. So if I have that memorized, or I go back to the very beginning and look at my chart, and I look for the perfect squares that will give me 64, turns out that that's the number 8. So if 8 squared is equal to 64, then the square root of 64 is equal to 8. That's how that works. And so coming back here, what we have is this is equal to negative 8. That's pretty straightforward. Okay, the next one is negative cubed root of 64. Well, since it's the cube root of a negative number, we know that number is going to be negative. But I need to find a k such that k cubed is equal to 64. Well, going back to my chart here, we're not talking about a square root anymore. We're talking about a cubed root. And if I go into the cubed column and find 64, this time it gives me a value of 4. So this must be negative 4. Moving on here and simplifying some of this stuff, we have the square root of 72 over 35. We should be able to rewrite that as the square root of 72 over the square root of 35. But now we're going to run into some trouble because neither 72 or 35 are perfect squares. In fact, if I go back up to this chart, nowhere on here is 72 and nowhere on here is 35. And so the question is, how can I simplify that any further? Those aren't perfect squares. Well, they're not perfect squares, but what we can do is we can take the number 72. We can do a prime factor tree. I need two numbers that multiply together to give me 72. How about 9 and 8? Where 9 is 3 times 3. That's a perfect square. And 8 is 2 times 4. And 4, That's 2 times 2. That's another perfect square. So if I rewrite 72 in terms of perfect squares, that's 9 times 4 times 2. The denominator is, well, 35 isn't too spectacular. Let's see. That's 5 and 7, so there's no perfect squares there, but I can rewrite it as 5 times 7. Now, what I can do here is use property number 1 that says I can break up the radical over multiplication. And so let me actually erase those two. What I can say is this is the square root of 9 times the square root of 4 times the square root of 2 over the square root of 5 times the square root of 7. And see if I can simplify this at all. Well, I know what the square root of 9 is. That's 3. The square root of 4 is 2. There's nothing I can do about that 2. And there's nothing I can do about the square root of 5 or the square root of 7. So if I now simplify this, I guess this simplifies as 6 root 2 over 35 is my simplified answer. Now, for this last one here, the cubed root, that's important, the cubed root of 360, what we want to do is we want to take 360 and find its prime factorization. 36 and 10, that's good. That one is 2 and 5. 36 is 3 times 12, and 12 is 4 times 3, and this is 2 times 2. So, in terms of perfect cubes and groupings, it looks like I have 3 powers of 2. So this is the cubed root of 2 times 2 times 2, or 8, 3 times 3, which is 9, and a 5. And I can break this up as the cube root of 8, excuse me, times the cubed root of 9, times the cube root of 5. And the only one of those numbers to appear on my perfect cube list is 8. This will be 2. And that's the most simplifying I can do there, this guy being 2. And then the best I can do there is maybe just combine those as the cube root of 9 times 5, which is 45. So that's what the cube root of 360 looks like. So there's a couple of examples of simplifying radicals that aren't perfect squares or cubes.